Hello everyone, another quick video here on circular motion, this time lesson 2, and we talk about the horizontal circular forces. So we're bringing in this idea of dynamics. As previously stated on prior videos, we have this concept in circular motion such that the velocities at any given point in time will be tangential to the circle, which means in order to continually change that velocity, there needs to be an accelerating force. So there's the acceleration, there's the force to the center of the circle. Indeed, that's what the word centripetal means. It means center seeking. So if that's the case, if we have an object in circular motion, we will be analyzing the sum of all forces, and that's what we have here as a statement. We're going to say that the sum of all forces in circular motion is centripetal force. So we can replace the F net with the F centripetal, and then it's just a case of looking at the dynamics of the system and seeing which directions those forces go. And in horizontal circular motion, it's nice and easy because there is only one direction. It's to the middle, okay? And then we just have to figure out what it is that's doing the force, what is actually applying the force, and then we can insert that in here, and it would be that would give us the centripetal force. So more on that to come in later lessons. We'll talk, when we get into the vertical circular motion, we'll be looking more at the directions and which forces to count. But for now, in horizontal, nice and easy. So let's look at a couple of quick questions and we should be done. So human centrifuge, this would be those fairground rides that you may have seen. It's kind of a spinning drum, and a human would stand inside and the thing gets going, and eventually you get stuck to the wall. And in some of these rides, the floor drops away and you're magically sort of stuck to the wall. Well, if we do a proper force analysis, once this human centrifuge is spinning around, obviously in a horizontal circular motion, we might just want to pay attention to some of the forces acting vertically. So we might do our X, Y analysis. So if we're looking at the vertical forces, this would be in equilibrium. If the floor's dropped away and you're sort of suspended, stuck to the wall, clearly there's going to be a force of gravity, and then that's going to be equal and opposite to this frictional force that would be coming from the interaction of the wall with the back of the human on this wall. Now, the force pushing the person to the center is going to be obviously directed to the center, so that is the direction. And that's actually going to be the normal force, okay? That's the surface, the wall, pushing against the back or the body of the person. That is pushing them to the middle. So that's the force normal. And as we've already established, all forces going to the center are going to be the centripetal forces. So when we look at let's do quickly on the y direction, our F net expression in the y direction is stationary. There's no acceleration, there's no motion. This is an F net equals 0, so that would mean that the Fg would equal the force of friction. Okay, nothing going on there. But this question is asking about the mass and the centripetal forces and giving us a diameter. Let's just note here, just so we don't forget, that a diameter is actually 2 radiuses, and it's asking for the time for one revolution, which is the period. So let's have a quick look at the x-axis direction. The F net in the x direction would give us this physics principle that the F net is equal to Fc, and that means we can say that 4 pi squared Rm over t squared is equal to this force normal pushing in. And we're given that value, so I'm just going to go and pop that value straight in. 5.21 kilonewtons. Okay, so nice and simple now, just algebra. We've done the physics. I'm going to plug these numbers in and I should get the result. So these are the numbers now plugged in. 4.5 is obviously half of the diameter. 76 is the mass of the human in the centrifuge. And then there's my 5.21 kilonewtons. Whole thing square rooted gives me 1.61 seconds. And that is to 3 significant figures. Okay, part 2. Now we have a car going round a bend. Now, this is a horizontal, so this is a flat track, and the car is turning in a uniform circle arc at a uniform speed. The question is, what is the maximum speed that that car can do? And we're given the coefficient of static friction. Well, the coefficient of static friction is to do with the forces pushing the car to the center, because of course the force that's acting on this car, moving it to the middle of the circle, or pushing it to the middle of the circle, is going to come from the tires, or the interaction of the tires on the tarmac, and that of course is friction. It's static because it's not skidding. As soon as it starts to skid, that would become the kinetic coefficient of friction, and it would no longer be in that uniform circular motion. So we're going right up to the limit of the tire's grip capability. Of course, we also have to think about the up and down forces, or the Y forces, which would be force of gravity down, force of normal up. And that's important because when we do an analysis in the horizontal and the Y direction, we want to think about the different physics that's going on. So as usual in the F net in the Y direction is going to be equal to 0, because it's in equilibrium. It's neither accelerating up nor down. And that means that we have this force of gravity being equal to the force normal. Now, force of gravity, of course, being mg. So mg is equal to the force normal. Okay. In the in the x direction, we have this physics principle that the sum of all forces is going to be equal to the centripetal force. And there is only one force acting on this horizontally, and that would be the force of friction. So we have this force centripetal being equal to the force of friction. And since we're interested in the speed of the car, we can safely assume that we're going to use this equation, v squared m over r, and that of course is equal to the force of friction. Now, we also know that the force of friction is equal to the normal force multiplied by the coefficient. So this is the first time we start to see this idea that we can substitute in part of our equations. So first of all, we're going to substitute this in for the force of friction. So that gives us Fn mu. And now we substitute in from the y coordinate in our equation. So we're going to take Fn and substitute that in. So that gives us the condition that's going to allow us to solve the question, which is v squared m over r is equal to mg mu. Now, what's neat about this is that you can, of course, cancel the masses out. So it actually doesn't matter what mass is going in the uniform circle, and that's going to be a common theme throughout this unit. The masses tend to cancel out quite often, so look for that. That gives us our final equation for V. I'll go ahead and plug those values in and we'll see what we get. So there we have it, just the rearrangement to get to V. I've gone ahead and called that the V max because it's at the maximum limit of the friction of the tires before it slips out and goes from static to kinetic friction. These are all the values and you get 22 meters per second.